You walked in yesterday. I hope you didn't erase it.
So the last important proof here of yesterday we proved the product rule and that d of somebody is 0, and now I want to do the fact that d commutes with pullback. So if G here is mapping some open set in Rn to Rm, and we had omega, a k-form on Rm, then I want to prove that if you pull back omega and get a k-form on U, and you take d of that, it's the same thing as first taking d of omega and then pulling back. So it sort of looks like a bunch of symbols put together, but you already saw yesterday why this sort of formula is important, because it's telling you that if you have a way of writing a form as being exact here, then when you pull it back, it had to be exact there. If you took a d of somebody that equaled your form, and you pulled it back, it would be, again, d of the pullback.
So the pullback of the exact form
is exact. And we're about closed while you're at it, Daniel.
Is it if I'm only in?
Yeah.
No, because you can't go back. You can only pull back. You can't push forward.
I would assume that a pullback closed form is closed as well, because of that formula right there.
Well, you should say you would assume. Can't you argue?
Well, the pullback of 0 is 0.
Right.
And then that means that d of the pullback of omega equals 0, which means omega
Good.
pullback of omega is 0.
That's perfect. Okay. So I'm going to do something very similar to what we did yesterday. I'm going to do a baby case, and then I'm going to say, oh, well, the general case is just the baby case with a little frill put on top of it. So what's the simplest case?
1.
K equals 0.
K equals 0. So what does that mean I'm starting with?
That's a new function.
A function. So let's let f be a function. What do I want to
Do we want m or n?
lives here, right? And then we're going to pull back.
Okay.
So the claim we want to make is what? That if I pull back df, it should be the same as taking d of the pullback of f. Now what is, you guys told me this several times yesterday, what is the pullback of f?
Well, hang on, isn't f doing the pullback?
No, g is in pullback.
It's like fog.
Okay.
The G star of F.
But then don't we need f from Rn to R?
Dan was confused today. I can see it's a bad day.
Alright, I'll just sit it out and I guess
You have
I'll
a
see
function here, pulling it back gives you a function there.
Okay.
And that's what composition is.
Okay.
Everybody agree? All right. Well, how do we take d of fog?
Is there a chain rule about you?
What do you think?
Yes.
So, by the chain rule, let's recall what the derivative of fog is.
So
df
df of g naught.
Valued.
Right? Yeah, right. Something.
All right, so let's do it at a point so we aren't getting confused. All right? The derivative of f composed of g at a is
df of g of a
df at g of a
times.
Times dg at
So how do I translate that into form notation? So this is a matrix, right? It's
Yes.
1 by m. And no, I lied. I totally lied. It's
It's 1 by n.
1 by n.
No, I totally lied.
It's 1 by 1.
No, F composed of G goes from Rn to R.
Right,
So
so
it's 1
this
by
is
N.
1 by n. Okay. What's df?
It's DF.
It goes from, it's 1 by N.
It's 1 by m. And what's dg?
It'll be N by
N by
something.
It's m by n, right? So, if I'm interested in the, say, jth entry here, how would I get it?
Taking the ith row of the first and the jth column of the
Wait,
second.
wait, 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 wait.
If you're looking for the ijth entry.
But there's only one row. So if I look for the
Okay, so
jth entry,
Then you're basically taking the dot product of the first,
that gradient.
of the transpose of that.
So I'm doing this whole thing times,
Dotted with the jth column.
I'll do the jth column there. Everybody agree? So what am I doing? I'm taking the partials of f with respect to, let's call them y's. So let's say we're using x's back here. I'm using letters different from what I've used before. I'm using x's here now and y's here. So let's put i's here. I don't want the same. All right. I take the partial of f with respect to y at g of whatever. This is at a point x. And then times what here? I'm doing the jth column,
So that's,
and I'm taking, so what am I doing? I'm taking the derivatives of g,
Well, specific derivatives of G at each entry.
so I'm doing the
dxj.
jth derivatives of g in its various components, g1, g2, g3, up to gm. So I'm multiplying the partial of gi with respect to xj times the partial of f with respect to yi and summing on I. So there's your dot product, right? So this is the hardest part of the whole argument, is rewriting our matrix stuff in terms of coordinates, which is not something we've done very often. All right, well, let's see. Why is that looking like this? So let's look at what df is. Well, df is
Sum of the partials.
the sum of the partials with respect to its variables times the corresponding d variable. Well, that looks good. That's this term, right?
What is one?
This and the,
Is that 2 and 5?
So the y's are the variables here, and the x's are the variables here. That's the notation I'm using. How do I pull back this one form by g? What's the rule?
You evaluate df of d whatever at g for composed of that.
And then I do what with the dy's? I have to do what with them?
They become dgi's.
They become dgi's. I have to pull them back. And that's the ith component here. So the way you pull back dyi is you take the ith component of g and you take its derivative. So the pullback of dyi is exactly dgi. Well, what is DGI? How do you take the derivative of a function? You take its partials times the corresponding dx's. So this is a sum on J, and this is a sum on I. How does this formula relate to what we have written down here?
Hopefully they're the same.
Well, we don't look quite the same.
Well, the df composed with g is the same as df evaluated at g on the sort of left-hand components.
Okay? So Daniel's saying that if I fixed a j here and summed on I, so this is a sum on I and then a sum on j, what he's saying is we could do it in the other order.
Is that times or is that a sum on?
That's DGI, so it's times. I mean, this involves I, so this is a sum of this whole thing on I. Okay? But now what I'm going to say is let's switch the order of the sums, and then maybe it looks more familiar. So I've got the partial f with respect to yi at g times the partial of gi with respect to xj, and then I'm going to sum that on dxj. So what's the coefficient of dxj? It's this sum where you vary I from 1 to m. This is the coefficient of dxj. Well, isn't that this sum?
Yeah.
So that means I have the sum of the partial of fog with respect to xj, dxj, which is d of fog. Yippee. So you told me the chain rule, and then I did the pullback, and in the middle of the pullback I rediscovered my chain rule and said, oh, well that's how I do the derivative of fog. Take its jth derivative times dxj in sum. Okay, that was the baby case. You guys look confused, but this it's just bookkeeping. I mean, this makes you appreciate how elegant the matrix notation for the chain rule is compared to the grunge that they do in engineering and physics. So this claim is just notation for the chain rule.
So how do you get from the last time you were multiplying two sigma statements to getting them nested?
Well, they were nested.
They were already nested.
This has an I, this has an I. And you're summing on I.
So how can you sort of move the
Yeah, how-
Because this is a finite sum. I'm summing finitely many terms, and I can
Yeah, so how are you?
rearrange
how
the
does-
sum of mn terms any way I want to. It's only infinite series you have to be careful about. Go on, Gabe.
Alright, so how are you getting from? Also, yeah. How are you getting from that step? They just.
All I did was I said, instead of doing the I sum on the outside and the J sum on the inside, this is like Fabini's theorem, that I'm doing finite sums here. I said, let's rewrite the order of sums where I put the J sum on the outside and the I sum on the inside. I'm still adding up the same m times n terms.
Okay.
It's just that I'm adding rows instead of columns first, or vice versa. Okay? So, I mean, it's yucky, but there's nothing deep going on here. It's just bookkeeping. turning this matrix, beautiful matrix notation for the chain rule into yucky component by component notation for the chain rule.
Does
All
anyone
right.
actually use that?
Hmm?
Does anyone actually use that grading notation that way?
This notation? Yeah. Everyone except mathematicians uses this. I mean, and a lot of mathematicians do too. No, I mean, it's all over physics and chemistry and engineering books, you find chain rule written out this way all the time. Except for they don't put the composition, they just do df, dyi, dyi, dxj, and sum. Right, Michael?
Yeah.
So is DGI, is that derivative? Yeah.
That's the derivative of g, ith component of g.
Up here, I guess I'm confused where you get this dxj at the bottom and the middle one.
This?
Yeah.
What do you mean? I mean, it was there.
So then,
That was how you take the derivative of a function on R and n. You take the partial respect to the n variables times the corresponding dx.
I guess I'm from this step to that step. So df over
This?
dyi
That was just this.
times.
He's subbing in there.
That's this.
This.
That was the chain rule. So that's the step where we substitute the chain rule. You guys might, I mean, I do this differently every year, but you guys might have been happier if I'd started on this side of the equation, which is how I usually do it. And then do this, and then say, oh, the chain rule tells me how to do this, that's this, and then regroup it and get back to this. So if you'd rather turn it upside down, rewrite your notes upside down. It's fine. Okay, that was the simple case. What's the hard case?
Similarly, k does not equal 0.
K does not equal 0. So I start with a general K form, and by now you should be used to what I'm going to say. How can we work with a K form on Rm? We may as well assume it's of what form?
A single term.
A single term. So again, because D commutes with sums and pullback commutes with sums, take omega to just be a single function times a wedge of dx's that has length k. Okay, how do we pull that back?
Well, it'll be
Or how do we take
f
d of it? Which side do you want us to start with? I'll let,
Take d of it.
which side, which do you want me to start? Which one do you want me to do?
Let's take that one.
This one. All right, so what's d of it?
df wedge dxi.
Okay, everybody agree? How do we pull back said d of it? How do you pull back a wedge of two things?
You wedge the pullbacks.
You wedge the pullbacks.
I could do things for you.
Now, do we happen to know what g pullback of df is?
Yeah, we do.
Because we just did it. So this is, by what we just done, did done. This is d of the pullback of f. Right, that's what we just did. Wedge, the pullback of dxi's. Now here we have to stop and think. So I'm not going to quite fit it on this board, although I could. What is the pullback of dx sub capital I?
It's the pullback of a bunch of things wedged together, so it'll be the wedge of all.
Okay, so Daniel's saying, let's actually think about what this means. It means I'm taking a bunch of dx's with various indices on them wedged together, and I'm pulling that back. How do I pull back?
You distribute. It'll be dgi1 wedge dgi2.
Right, so you just pull back by using what we just used, that the pullback of a certain dx is the d of that component function of g. So this is what I would write as dgi. Right, just by analogy with using the subscript on x, you're using the exact same subscript on the g.
Do those still have pullback stars?
No.
I think he means, no,
I'm using the same thing I used there. The pullback of
you're,
d
you're
somebody.
missing a pullback star
At the
just at the
top,
top. It's
G.
just on the
Oh.
right side
Yeah.
there.
Now what are we supposed to be getting? We're supposed to be asking, what do we get if we do the d of the pullback of omega? So on the other hand, what is the other side? That's d of the pullback of f dxi. How do I pull back f dxi? Okay, or I pull back f, yeah. And then I pull back the dxi's, well that's just exactly this, isn't it? Right, that's what we just said. The way we pull back dxi, that's what I just did here, is dgi. Well, what does the product rule say for this?
Oh, because the 2D's are going to go to 0. Okay, so D, G pullback F, wedge, the DGI, and then plus
-1.
Well, there is no -1 because this is a
G.
function.
G pullback of F.
D of this bunch of dg's wedged together.
Which is 0.
Now, so remember, the D of the bunch of dg's wedged together is this. I1 up to ik. How do you take D of a wedge?
Well, but it's going to be 0.
It's going to be 0. It's actually k0 is added or subtracted. Right? By the product rule, you do D of the first thing, wedge the rest. And then you do a minus sign that, and then the D of the middle one, and so on. But these are all D somebody. So if you do D again,
So 0.
Do you have a minus sign for each term is it the first, or do you?
alternating. Alternates. Because when you get to the third one, you've gone across 2, so you get a -1 squared. When you get to the fourth one, you've gone across 3, so you get. So this is sum of plus or minus terms that look like D of one of the ones in the middle. Okay, so this is a sum as you go through all of the ones, plus or minus, but each of these things is 0 because D of somebody is 0.
Could we just say, rather than having to think, could we just say that D of dg would be a k+1 form, and
No, you're not getting out of it this way.
what is g?
No, you're not getting out of it that way.
Okay.
Because k can be any number. No, it's specifically because these are wedging together exact one forms. So when you take D of a product of such things, it's 0 by your homework. You prove the wedge of 2 exact things is, again, exact, which means D of it is 0. Okay, so we're done because this is 0, and this matches this. Because of this comment. So All right, this is not very inspiring, but it's done. Hmm?
Sorry, one more time. Why can't you just know that since you have d of r, since you already have d of a derivative, you can, isn't that always 0? D dg.
But this is, yes,
I know you
but
can
this
do
is a wedge of them, and I needed to argue that if you take a wedge of derivatives, d of it is still 0 because of that product rule you're saying. Because of the product rule together with what you're saying.
Okay.
Or, I mean, there are other ways around this.
Well, I think what he's asking is it's DGI, you know, D of phi for some function phi.
It's d of g, I.
Yeah. So can't
So
can't you just say that that's
Well, that's what I'm using. It's d of a function, so d of it is 0. I'm using that, but, all right, if you guys don't want to use the product rule to do this wedge product, you could also notice if by your homework, well, you don't really need homework, I'm just going to sort of give it away here. DGI is d of the first one without the d in it. Just take the function gi1 and then take dgi2 wedge dgik. I mean, it's the same argument.
why are you only distributing one derivative to the wedge product?
Right now, because by the same observation, if I take d of a function times d thingies, I get d of the first term,
Yeah.
wedge that, and then I get this times d of that.
Okay.
So I'm removing the product rule one level here. So this is already exact.
Okay.
So d of it is 0. It's the same argument, really. Okay, I'm sick of this. Let's move on. So basically, the fact that d of somebody is 0 is just a jazzed up proof using mixed partials being equal. Right, we used the mixed partials being equal to do that proof yesterday. And this thing is just the jazzed up chain rule. So this property is just chain rule plus a pile of notation. The fact that d of somebody is 0 is just mixed partials being equal plus a bunch of notation. So those are the two key things underlying all this stuff that's going to make it all work. All right, so why do we care about this? Daniel asks.
well, not in that tone of voice.
So why do we care? Well, I already pointed this out to you, but I'm going to point it out again. The change of variables theorem which ranks up with the inverse function theorem is very important, said what? It said that if we had a C1 function from and set in Rn to Rn, same dimension, and we had a region omega contained in U so that G is 1 to 1 on that region. Remember what it said? It said integrating over G of that region, which we call S, as I recall. Oh, this is on your test on Thursday, isn't it? How convenient. Change of variables theorem.
I hated the way you said
That's actually a test
that.
question. Yeah, but no.
So it's like
F of x dv. So I didn't write it with the of x, but I'm reminding you that we have x variables here now and u variables there. This is how we wrote it. We said you could integrate over the region back here, fog times fudge factor. And what was the fudge factor?
Determine the
Absolute
ADG.
value.
Absolute value. Times volume in U space. Now this, at this point, should be reminding you, and I think I talked about this yesterday briefly, or Friday, I don't remember which one. this should be reminding you of what we've been doing. If you formally take the n form on Rn given by f of x dx1 wedge dxn.
So that can only be one. There can only be one after this.
Yeah, because I'm doing n form on Rn, so I'm using all of the x's. That's a one-dimensional vector space. Lambda n of Rn star is one-dimensional. But now if I pull back, it looks notationally, okay, so this dv magically turned into an n form. I don't know what that means. We'll get to that in a second. But if I pull back this, what do I get? Well, I pull back the function, I get fog, and then I pull back the dx's. That's taking the pullback of each of the dx's by the components of g. And what do you get if you wedge all the dg's together? You get the determinant of the derivative matrix. Times the du's all wedged together. So remember, the magic of differential forms is that we're building in determinants everywhere. And in particular, that when you're doing these minors of the derivative matrix, when you have all n of them, you're doing the whole derivative of the whole matrix taking determinant. Well, that looks mighty like this, except for one thing. The absolute value bars. Oh, who cares about absolute value anyway?
Yeah.
So, if, underlined, determinant of dg is positive, then I can ignore the absolute value bars. Agreed?
Mm-hmm.
This is looking like it's matching this if I forget the absolute value bars, provided provided I tell you what it means to take an n form and integrate it. So the definition is as follows.
It's one of those functions that's just star.
No, because this is just, no. You're going to know this. All right, so the definition is this. The integral over a region, over a region in Rn of, I'm getting worried about using omega. So let me say it this way. Let S be a region in Rn, and let omega be an n form.
That
Defined on an open set in Rn where S is contained in that open set. I'm being pedantic here. But what I want to define is the integral of omega over S. And the convention is, here's your n form. The way you integrate an n form over an n-dimensional chunk of Rn is you just integrate the function. You forget about the n form and you just think of it as a regular volume integral.
What's the point of all of these dx's?
The point is that you've built the change of variables theorem into the whole machinery, so that so I'm going to get there. All right, now the only warning here, before I deal with what Ken's asking, is, and this is going to be very important, so star this if you want, because this is important. You must put the dx's in the standard order.
Super.
It's like that after
That's what you have to say, like.
It's related, yeah. So this bothered me no end when I was learning this stuff as a student, as you are now, because I said to myself,
So,
I could write f dx wedge dy as minus f dy wedge dx. How would I know whether to integrate f or minus f to do this? Well, the rule is put the things in the standard order first, then just pluck off the function and do the integral. Now, Ken asked, why are we making a big deal out of all this? Well, the big deal is that the change of variables theorem says that if you have what's called an orientation preserving map, that's what this means, then pulling back and integrating is the same as integrating in the first place. So,
That definition is only for the determinant of
so say again?
That definition is only for the determinant greater than 0.
No,
Oh, it
that
can
definition doesn't involve that.
Never
That was just for an end form to start with. So now, the point is, that the change of variables theorem says if determinant of dg is positive, and the language, as I said, for this is saying g is orientation preserving, and we'll see what this means soon. Then integrating f times dx1 with dxn over g of omega is the same thing as pulling back that n form and integrating it over omega. So that's the change of variables theorem. It says, with this mild condition, which you'll understand more as we go on for the next few weeks after spring break, with this mild condition, integrating the n form is the same as pulling back and integrating the n form. Because
On different regions.
on different regions. Right, so here it's exactly matching, right? You pull back to omega in the range you were integrating over g of omega. So what this is going to allow me to do is to define integrals on manifolds. So this is going to allow us to define the integral of a k-form over a k-dimensional manifold. So omega a k-form m, I'm going to have to tell you eventually what it means to have an oriented manifold. It's k-dimensional. So this is what's coming up. But what I'm going to do today is just a baby step.
So now when they're graded,
Take a lot of really long.
You said the differential forms were a fairly recent concept, right?
Well,
So,
turn of the 20th century.
so before this, even though manifolds were, I guess, understood, they couldn't integrate over them before then? Or did they just cut out the proofs and say, we can do this, we know it's right, but we don't know why?
Actually, okay, that's a great, no, so certainly Gauss thought about integrating over manifolds, but he did it locally. That's a great question. I think to some extent people did stuff procedurally without being as hyper rigorous about it, but I'll actually have to look up the history on this to get the time right. That's a great question. So the intermediate step that I'm going to do that's going to carry us through sections 3 and 4 before we worry about this is let's talk about the case where M is a parametrized k-dimensional manifold. So for example, you can parameterize a curve that goes from one point to another. And notice that that curve is not officially a manifold because near these points it doesn't look like it has a neighborhood that's parameterized by an open set. So I'm fudging a little bit here. But what I'm going to do is say, if you have something like a curve or a hemisphere or a piece of paraboloid or a closed curve, whatever, that we're going to be able to make sense of defining an integral of a k-form over one of these k-dimensional objects by setting. So if M is an Rn and omega is a k-form, okay, M is k-dimensional, and omega is a k-form on Rn, define the integral of omega over M by pulling back by your parameterization and integrating over your region. So G, I said M is a parameterized manifold. That means you've got some domain that's parameterizing it. So I'm going to say you parameterize M in some way by some function G. So it's fitting the third definition of the manifold definition. Then I'll pull back and I'll integrate. So I'm going to turn an integral over M into a regular k-dimensional integral that you've been doing since chapter 7. And the remark, and I'm going to spare you this because you don't want to hear the technicalities, but the remark is that the change of variables theorem tells us this is well defined.
So how is that integral on the right easier? You said.
Because then you're just integrating over an open subset. Sorry, I should have said this in RK.
But what if U is some complicated manifold?
It's not a manifold. It's a region or an open set in RK. Same dimension. That's what parameterizations are, right? They're mappings from open sets in RK. So the change of variables theorem is going to say, so the technicality here is that if you took one parameterization and I took a different one, how do we know we get the same answer? Well, the point is because you have a parameterization, it's a one-to-one mapping, and you can do the inverse of one followed by the other. So I can do, for example, G2 composed with G1 inverse. No, I got it wrong. G2 inverse composed with G1. So I can go here and here, do change of variables here, and it's going to tell me exactly that I get the same answer when I pull back here and I pull back here. So I'm not going to do this proof because you guys don't want to see it. It's sketched in the book, and it uses, there's a little bit of technicality, but I don't want to do it. So basically the key point is going to be that, and I'll mention this explicitly in an example tomorrow, that no matter how you parameterize, you're going to get the same answer. And that's the beauty of pullback. So the whole point of all this differential forms material is that it makes this be true. The fudge factors are all built into the pullback. And that's what's telling you that if you do two different parameterizations, you get the same answer when you pull back and integrate. All right, so for the next few days, we're just going to do it with one forms and integrals on curves. So there will be web work on all of this, of course.
This weekend?
And it's not due this weekend because spring break starts this weekend. So, the word that people use, and I've never understood why, is line integrals. You're not integrating on lines. Well, some books call them path integrals. You're integrating on paths, or you're integrating on curves. So, say you have a parameterized curve in Rn. So you have a
Definition.
yeah, so let's see the curve that you get by taking this parameterization. So this is the kind of thing we were doing last semester when we were talking about parametric equations, for example. So you have a parameterization of some weird curve, and if I take a one form on Rn, then I ought to be able to define how you would integrate the one form on the curve C. Okay? One form, one dimensional. Pull back. This is like what we were actually doing yesterday, although you didn't know it at the time. When you pull back omega, you have a one form on the closed interval AB. Well, you can just do the integral like you did in Calculus 1 or Calculus 2. So this is how you define it. So what's the formula for this? So if omega looked like F1, I'll actually use capital F's for reasons that will soon be apparent. So if your one form looks like a bunch of functions times dx's, there's no subcapital I because I just have a 1 index, so there's 1, 2, up to n. Then what do I get when I pull back?
So F1 composed of G and G1.
So yes, I'm going to get lazy at this point and put a summation symbol. You're going to get the ith f at g of t. Right? Plug in the function at g of whatever, times the pullback of dxi. Well, how do we pull back dxi? You take dgi, and what is that? It's a function of one variable. Stop it, board. You just take the derivative times dt. Right? The function g here has n component functions. To take the derivative of one of those component functions, you just take its usual derivative dt. But now you say to yourself, this looks remarkably like... No. Good. I see why you said that. Guess again.
I don't want that.
Summation AI BI.
No, I don't want to say it. Say it.
Say it.
dot product?
Yeah. See? Staying awake was all right. This is a dot product of the vector field you get by putting the f's into a vector with the vector g prime of t. So this one form gives us n functions. Instead of thinking of those n functions as coefficients of dx's, I can think of them as coordinates of a vector.
So then we just have the vector function.
So capital F, remember I think I used the word vector field back in chapter 2 when we were first talking about this. This is a vector function, so this one form omega is corresponding to a vector field on Rn, a vector function.
So a vector field is just a vector value function.
Yep. So now F is mapping Rn to Rn, given by these components. And you're computing the vector field at each point and dotting with the velocity vector. So what is that doing geometrically? It's saying, here I am at a point on the curve. I've got my velocity vector as I move along the curve. And I've also got my vector field at that point, which who knows what it's pointing like. And I'm doing the dot product. So people in here who have had physics should already be recognizing this.
Flow or circulation?
No, well, not quite. You're asking how much,
Well, how much stuff is flowing along the line?
you're asking how much of F is pointing in the direction of the curve. So when you integrate this omega, the notation that is used in standard calculus books, well, so the definition here is I'm going to integrate f of g of t dot g prime of t dt. So that's how you actually compute it. If somebody hands you the one form and says compute this integral, this is how you compute it. But now I'm about to give you the physical interpretation of it, and I'm going to real quick today. A bunch of examples tomorrow.
Is that flux?
No, it's not flux. So you're taking f, and you're asking, in some sense, you wish that this were, instead of a velocity vector, you wish it were a unit vector. Because then if you dot a vector with a unit vector, you know what that means. If you dot a vector with a unit vector, you're saying what's the component in the direction of the unit vector. So I want to rewrite this as f at g of t dot the unit vector in the direction of the velocity. Well, I can't just do that.
You have to multiply by the magnitude.
I have to multiply back by what I just divided through by. So this now becomes the dot product of f with the unit tangent vector to the curve.
Why do you like the C?
Because I'm erasing all the t's, the little t's. You'll see. I'm taking the dot product of the vector field with the unit tangent, and then I'm integrating not with respect to t, but with respect to what? What did we do last semester? It's on top of things. This is arc length. Integrating speed gives you distance traveled. So the standard notation here is that you're integrating f dot t ds, where s stands for element of arc length, where ds stands for element of arc length. So you're taking how much of the force is pushing you tangent to the curve and adding that up along the length of the curve. And for reasons I will explain tomorrow, this is called the work done by f along the curve. So you can imagine an imaginary little particle piece of styrofoam that F is pushing along this wire. And what this integral is going to compute, as I will show you tomorrow, is how much energy F added to the particle. So work is going to tell you change in energy. Okay, so we'll do that tomorrow and do lots of examples.